Hello everyone, I'm Hanji from Xi'an University. Our team participated in the third task, multi-object tracking. I'd like to introduce you our method, cost to find multi-class multi-object tracking. Cost to find multi-class multi-object tracking aims to locate the positions of multiple multi-class targets, such as car, bus, pedestrian, truck, and van, and maintain their identities in different scenarios. The key insight of our proposed method, COFE, is that event targets are interactive and mutually occluded in crowd scenes. They are semantically discriminative in cost categories. For example, pedestrians and buses may be intricate in a traffic jam, so directly tracking the targets of all categories are difficult, and their motion and locations are hard to distinguish. Nevertheless, it is still possible to estimate the cost category, people or vehicle of each target, and allows us to eliminate the target occurrence and interaction by tracking targets in different cost categories respectively. On this basis, we propose the COFE-MC-MOT method to track targets in different categories, where we first track targets in each cost category and then fine-tune the obtained trajectories for each fine-grained subcategory, which can eliminate target interactions in complex scenarios, while remain the capacity of fine-grained object tracking. The proposed method, COFE, contains three major modules: multi-class object detection, cross-category multi-object tracking, and fine-grained trajectory fine-tuning. Firstly, we use a deep convolutional neural network-based object detector to detect interested targets in the image plane, where each detection is denoted by a bounding box with a class label and a confidence score. Secondly, we track multiple targets in cost categories, where fine-grained classes such as van, bus, car are summarized into cost categories, vehicle. For each cost category, we perform multi-object tracking by exploiting the appearance and motion information of targets, where the appearance feature is extracted using a deep convolutional neural network feature extractor, and the motion pattern of each target is modeled by a Kalman filter. Finally, for each obtained trajectory from Module 2, we fine-tune its fine-grained class label with a simple vote mechanism and refine the tracking results by post-processing, such as trajectory padding and smoothing. In the multiple class object detection, we adopt Cascade RCNN and our baseline because of its outstanding performance in many object detection competitions, and choose ResNet 50 and the backbone, which we have pre-trained on COCO 2017 training dataset. To handle the problem of detecting objects at different scales, we adopt FPN and the NIC, and introduce deformable convolutional networks to adapt to complex geometric deformation. In the course category multi-object tracking, we first summarize fine-grained classes van, bus, car, and truck into course category vehicle and get two course categories vehicle and pedestrian, and then link the course class detections into course categories trajectories using appearance and motion information, and solve the data association problem by a Hungarian algorithm. We extract appearance features by OSNet, which is pre-trained on MT17 dataset, and the motion pattern of each target is modeled by a Kalman filter. After getting the appearance and motion information, we use a matching cascade that gives priority to more frequently seen objects to link detections into course categories trajectories. This can include our notion of probability spread in the association likelihood to help us avoid the following situation. When an object is occluded for a longer period of time, subsequent Kalman filter predictions increase the uncertainty associated with the object location. Consequently, probability mass spreads out in state space, and the observation likelihood becomes less peaked. In the fine-grained trajectory fine-tuning, we fine-tune its fine-grained class label by voting on the class label of each trajectory according to the coarse-grained results obtained by Module 2. For example, for trajectory I, its class labels include 20 buses, 5 cars, and 3 trucks. Then we vote that bus is trajectory I's final class label. Then we refine the tracking results by post-processing, such as trajectory padding and smoothing. Our COFE method achieved the best result in the VisDrone 2020 challenge and significantly outperforms most of the competitive methods by a large margin. Thanks.